So this problem we saw of the collapsing cylinder is the actual Rossby adjustment problem, where we are looking for the balance between rotational and stratification effects, right? So this was our lab setup. You can think this was our lab setup. In the real world, you can think of pole with so now we are looking at a different section through the pole. Pole is in the middle. You're going at different latitudes, and you can see here is our similar structure of currents going into the page and currents coming out of the page. So you have this jet stream that circumnavigates the Earth at some height in the upper atmosphere, and we have our thermal winds and the vertical shear, and you have your nice cold air mass sitting on the pole, right? So it's essentially the same. The cold heavy air wants to collapse by gravitational pull, but the rotational effects keep it bound, just like this in the lab that we saw. So it's amazing analog for the real world, even though we did it here with a simple setup and the water tank and heavy salt water versus normal water, right? But you can see the clarity of concepts carry through. So here we had the adjustment starting, and then the adjustment ends with this currents across the parallel to the front, just like we have winds parallel to the front happening here, right? So this is the adjusted state. This is the adjusted state where small frictional forces in the lab will eventually do something, but in the real world you have this constant energy transport maintaining the contrasts as well. So not exactly the same, but essentially the same. So let's do the radial balance in the lab as for the Rossby adjustment problem. We'll see that Rossby is this big name in our business of atmosphere and ocean circulation. Carl Gustav Rossby was a giant in the field. Okay, we'll see that a little bit later on. So omega r squared plus ur equal constant. What is this? This is our angular momentum conservation. We have the rotational azimuthal speed because of the rotation of the tank, and then relative to the tank. So this is similar to our v theta plus omega r. Remember, it's the same, and we multiply by r because angular momentum depends on the distance from the axis of rotation. So that's our setup, and we look at the adjusted state where we had deviation of delta r from the initial state. So if you had angular momentum when the cylinder was standing up, then you want to see if how the angular momentum conservation works when the cylinder has collapsed and reached the equilibrated speed, right? So azimuthal speed is again given by u. So this is now the relative change because of the cylinder collapse. Okay, so you're taking this equation, and omega r squared is essentially the same. So you have changed delta r, which means you have moved the water parcel either towards the axis of rotation or away from the axis of rotation. So this is our axis of rotation. You have moved it towards the axis of rotation here and away from the axis of rotation here, and that's the perturbation to the angular momentum, right? So that's what we are looking at here. U equals minus 2 omega times delta r. That's the azimuthal velocity introduced by the changes. So going back to our Margulis relation, u2 minus u1 equals g prime tan omega over 2 gamma, where omega is the angle of the cone. the front. G prime is our reduced gravity, and omega, of course, is our rotation rate, right? U2 minus U1 is the difference in the velocity across the front. Okay, here we can estimate tan gamma as h over delta r, where h is our height of the water column. So h over delta r gives us tan omega as an approximation, and delta r magnitude, because for the top part delta r is negative, for the bottom part delta r is positive. So 721 and the introduced perturbation azimuthal velocity can be combined, because this is essentially u2 minus u1, right? The change across the front created by the slumping. So the slumping will continue till the vertical shear u2 minus u1 is enough to balance this gravitational pull, right? Remember, this is the reduced gravity which is pulling down the cone, heavier water, and rotation is modifying this. So that's the balance we are looking for, and this will happen when delta r is equal to square root of g prime h. H is the height of our water column. You can think of it as our old scale height, remember, divided by 2 omega. Okay, that we got just from this relation. Okay, combine this and this to get the delta r. How much the cylinder has to collapse to accomplish this balance between the rotational effect and the gravitational effect. Okay, so this is like a frequency. It's called the buoyancy frequency. Why? Because we again have our familiar g over rho d rho. That's the relative frequency of oscillation you will get. How do you think about it? Essentially, think that there is a stratified fluid. Gravity is pulling down, but buoyancy is balanced by the water, heavier water being below. So you are lighter, buoyancy is keeping you up, gravity is trying to pull you down. But if you displace the water parcel down or up, then your buoyancy and your gravity are not balanced anymore. So let's say your heavier water is moved up. It's heavier compared to the water around it, so it's going to sink. Its buoyancy is reduced, so it's going to sink, but it's going to overshoot and it's going to come back up, and you're going to get these oscillations. Those are the buoyancy frequencies. So obviously it looks like minus g over rho dz, and replacing d rho dz with our equations as we derived before, n squared just becomes g prime over h, so delta rho over delta z. Okay, so n squared is minus g over rho delta rho, so minus g over rho delta rho is g prime. We absorbed it into delta z over h. Okay, h is our so we have replaced the relation of delta r and h from here. Okay, so I hope it's clear. I'm not saying it very clearly. So n squared is our buoyancy frequency, and this is a length scale. It's a Rossby radius of deformation, as it is referred to. Okay, so we'll see what that means. So here our g prime is g delta rho over rho, and g prime h, you can write g prime h is, you can divide by h and multiply by h. So take h on this side, so you get n squared h squared equals square root gh. So then our L rho essentially becomes square root g prime h over 2 sigma becomes nh over 2 sigma, where h is the vertical scale of motion. Okay, Is that clear? I hope it is. You just look through the equations again. So this is the length scale over which delta R, which is required to balance stratification or gravitational pull versus rotation. Okay, it's the horizontal length scale called Rossby radius of deformation. Okay, so this problem is called the Rossby adjustment problem. How does it work? Basically, if you introduce perturbations into the system, then we have to see how the velocity field and the pressure field adjust to each other in that case. Okay, so the system is balanced. You introduce a perturbation and the system adjusts back to equilibrium on a large scale balance sense we have been talking about. So what are the changes that occur in this readjustment? Okay, that's the Rossby adjustment problem, and it depends on stratification, as we saw, because oops, I already closed it, but nonetheless we had the stratification term delta rho over rho, and we had the scale height. Okay, so those are the critical quantities. We'll look at this in a more realistic setting in the next podcast, but just get the concept of Rossby adjustment, similar to the cylinder collapse in the lab, but in the real world it is the adjustment of various forms of perturbations, including the cylinder collapse of the cold polar air.